Okay.
Hi, my name is Brendan, and I'm here with my partner Matthew. Today we'll be teaching a lesson on electrochemistry. Hope you enjoy. Lesson 1. Describing reduction/oxidation processes. Before we start, we'll need to know some definitions. Number 1. Half reactions. A reaction that occurs in a half cell, also known as a half cell reaction. A half cell reaction occurs in an electrochemical cell. Number 2. Oxidation reaction. A half reaction where a species loses electrons. And lastly, reduction reaction. A half reaction where a species gains electrons. For this section, we'll be looking at half reactions. A very important point to remember is oxidation reactions lose electrons and reduction reactions gain electrons. An easy way to remember this is the acronym Leo the Lion says GER. Leo stands for loss of electrons is oxidation, and GER stands for gain of electrons is reduction. The complete reaction that occurs in an electrochemical cell is known as a redox reaction. Also note that when you see an ion/atom change during a reaction, you can be certain you're dealing with a redox reaction. For every oxidation reaction, there must be a reduction reaction to accompany it for it to be a proper redox reaction. Now, how does this oxidation/reduction process work? In simple terms, think of it as electrons being transferred from one substance to another. An example of a redox equation is Fe2 plus Sn4 plus equals Sn2 plus 2Fe3 plus. To tell whether a species is being oxidized or reduced, let's look at our memory aid again. Leo the Lion says GER. Since the oxidation is the process where an atom/ion loses electrons, you'll know it is an oxidation reaction when the products have a higher charge than the reactants. In other words, when an atom/ion becomes more positively charged, it is an oxidation reaction. As for reduction, as one would expect, it is the opposite. Since reduction is a process where an atom/ion gains electrons, you will know it is a reduction reaction when the reactants have a higher charge than the products. In other words, when an atom/ion becomes more negatively charged, it is a reduction reaction. The last thing we need to know about reduction and oxidation reactions is oxidation numbers. Oxidation numbers are used to keep track of how many electrons an atom has. However, they don't always translate directly into the actual charges of molecules. We can use oxidation numbers to compare ions/atoms to see if they've reduced or oxidized. The rules for determining oxidation numbers are in this slide. Although it may seem straightforward, there are a couple of exceptions. In neutral compounds, oxygen has an oxidation number of -1, and in metal hydrides, hydrogen has an oxidation number of -1. That is all for lesson 1. For our first example, above is the redox reaction equation, and below is our reasoning. Now, we'll be moving on to our practice problems. Number 1. In the following reaction, indicate the species oxidized, species reduced, oxidizing agent, and reducing agent. In the equation 2Li plus F2 into 2Li plus 2Fi minus, two species are changing their electrical charge during the course of the reaction. Since Li is losing electrons, becoming more positively charged, it is being oxidized. Since F2 is gaining electrons, becoming more negatively charged, it is being reduced. Finally, since Li is being oxidized, it is a reducing agent. And since F2 is being reduced, it's the oxidizing agent. Number 2. Find the oxidation number of Cr in Cr2O7 2- ion. For this example, you know the oxidation of O and have the charge of the ion. Put the charge, -2, on the right side of the equal sign and write out the Cr and O on the other side. Don't forget your subscripts. Plug in the oxidation number of O and then do the simple algebra to get your answer. You should end up with the oxidation number 6. That is all for our examples and practice questions in lesson 1.
Alright, moving on to practical use of electrochemical cells. Electrochemical cells have many uses in the technological industry, especially in the making of electrical batteries. An electrical battery is a device made of one or more electrochemical cells, also known as galvanic cells or a series of cells, that stores chemical energy and converts it into electrical energy when needed. Primary batteries are single-use batteries that cannot be recharged. An example of a primary battery is a zinc-carbon dry cell. A dry cell contains zinc, which can act as a container, a negative electrode, and a positive electrode made of carbon. The anode is surrounded by manganese oxide, zinc chloride, ammonium chloride, and a carbon powder paste, as well as a small amount of water. Initially, all batteries, D, C, A, AA, and AAA, have a cell potential of 1.5 volts, which decreases over time with use. They are manufactured in a way so that they have a very low self-discharge rate, unlike secondary batteries. Another example of a primary battery is an alkaline battery, which is able to deliver 3 to 5 times the amount of energy a zinc-carbon battery can make. These types of batteries should not be left in electronic devices and should be removed to store for long term, as they are prone to leaking potassium hydroxide, which is very toxic. Secondary batteries. These are rechargeable batteries used in devices such as phones and cars. An example of a secondary battery is a nickel-cadmium battery, which is made out of nickel-plated cathodes, a cadmium-plated anode, and a potassium hydroxide electrode. A separator prevents the shortening of positive and negative plates and is rolled together with the positive and negative plates in a case. This roll-up design enables the NICD cell to deliver much more current compared to the primary battery, like an alkaline battery. The voltage of an NICD battery ranges from 1.2 to 1.25 volts and can be recharged up to 1,000 times. Next, we'll talk about some other type of batteries. Lithium batteries are another popular type of rechargeable battery that are commonly used in smaller and more portable devices, such as phones. The battery voltage is about 3.7 volts, and they are popular because lithium batteries are relatively light and provide a large amount of current. They provide almost a constant voltage, and when they discharge, only lose a little bit of the charge when stored. The lead-acid battery is the last type of battery we're going to look at today, and is a secondary battery found in automobiles as they are inexpensive and can provide a huge amount of current. Each cell produces around 2 volts, so if 7 cells are connected in series, a 14-volt battery results. These batteries are very heavy and contain a caustic liquid electrolyte, as well as high levels of lead. So lead-acid batteries must be disposed of properly and handled with care. Next, we have some example questions. So what happens when zinc in the container oxidizes? So as oxidation occurs, its contents will leak out over time. This is why zinc-carbon batteries should not be left in electronic devices for a long period of time. This one here. Is it safe to throw out NICD batteries into a regular trash can or open them? No. Cadmium is a very toxic heavy metal and known to cause cancer and damage the body's cardiovascular, renal, gastrointestinal, neurological, reproductive, and respiratory systems, even with a very short exposure, so you have to be careful with them. And that concludes Lesson 2.
Lesson 3. Predicting whether a spontaneous redox reaction will occur. Note that some of the subscripts weren't working, so excuse the messy layout. To predict whether a redox reaction will be spontaneous or not, you'll have to look at the standard reduction potential table, which works like the relative strength of acids table. Depending on where you find the reactants, a variety of things could occur. Option number 1. If you find both reactants on the left side or both reactants on the right side of the table, no reaction is possible. This is because you need both a reducing agent and an oxidizing agent to have a complete redox reaction. For example, if you had only copper and Br in the reactants, no reaction could occur since both can only oxidize. Option number 2. If you find the reactants on different sides of the tables, one left and one right, 2 things could occur. Scenario number 1. If the oxidizing agent, the one that's going to be reduced, is higher than your reducing agent, the one that's going to be oxidized, on the table, your reaction will be spontaneous, 100% to completion. Scenario number 2. If the reducing agent is higher than your oxidizing agent on the table, your reaction will not occur, 0% tendency to react.
Alright, in summary, for a reaction to be spontaneous, the oxidizing agent must be above the reducing agent, and be on opposing sides of the standard reduction potential table. Next, we have some more examples and practice questions. So, example 1. Here we go. Here is the question, and this is the explanation. Moving on, let's do some practice questions. So, identify as spontaneous or no reaction. Write out the complete reaction if spontaneous for AgI-. So both species can only be oxidized, that means they're on the left side of the table, therefore no reaction can occur. Next, which of these species is a stronger oxidizing agent? So the species higher on the left side of the table has a greater tendency to reduce, which means it would be the stronger oxidizing agent. In this case, Br2 is higher on the left side of the table, and therefore it is a stronger oxidizing agent. Since Br2 has a voltage of 1.09 volts, and I2 has a voltage of 0.54 volts, that means that it has a lower tendency to oxidize. So that concludes our lesson on chemistry. I hope you enjoyed, and have a great day.